All right. So we're in section, what are we, 2.4 today. Now, because of the way we do the class here, we already talked a little bit about complex numbers first semester. We talked about in trig form, and we talked about them kind of when we talked about vectors and we talked about the angles and all that kind of thing. We're not doing that today. We're just talking about complex numbers in standard form. Normally you do chapter 2 before you do chapter 6, but we turn it around a little bit. All right, so complex numbers come up because, and we're talking about them when we're talking about solving polynomials, because even a simple equation like x squared plus 1 equals 0, we can't find a solution with real numbers because we'd end up taking the square root of -1. So if we were trying to solve this, we'd get no real solution. Now, interestingly, complex numbers, imaginary numbers, originally came up not from solving this equation, but we're trying to come up with a formula like the quadratic formula for a cubic equation. And it turns out for cubic equations, even if all of the solutions are real, the intermediate steps in finding the solutions involve complex numbers. So the idea of complex numbers, or the imaginary numbers, originally came out of solving cubic equations that have real solutions, but in between you end up having to use complex numbers, which is kind of interesting, kind of hidden inside those cubic equations. So what mathematicians did, and at first a lot of mathematicians didn't really think that it was a great thing, we said, well, we need more numbers. So we said, we came up with this number, mathematicians came up with this number, where I was the square root of -1. And if that's the case, it has this nice property that I squared equals -1. So we call I the imaginary unit. And it's kind of unfortunate that they called these imaginary numbers. They could have called them anything, really. I always tell students we could call them Fred numbers, because a lot of people think, well, imaginary means they're made up. It just means they're not real numbers. So they kind of the opposite of real is imaginary. That's just the word that they ended up using, is imaginary. But they could have been, we could have called them Fred numbers. And this would be Fred is the square root of -1, Fred squared is -1. We could have called it anything.
If they're not real, if they're not imaginary, what are they?
Just some other kind of number. And real, when we say real numbers, it doesn't necessarily mean real in the sense that we use the everyday word, like it exists and we can hold on to them. That's just the name we gave it. Real numbers. All right. So we call Beamer squared. Yeah, Beamer squared. We call, so I is the imaginary unit. And if we add a real number to multiples of this imaginary unit, we get complex numbers. So complex numbers are numbers that look like A plus BI, where A and B are both real numbers. So we call this a complex number. We call this the real part, and B is the imaginary part. So the part, this piece is the is the imaginary part. So we have our complex numbers have two pieces, and we call this, when we write it in a plus bi, when we write it like this is called standard form. And our book always writes complex numbers in standard form. And I'll talk about where we might do it a little differently sometimes, and it's fine. All right. So if we have two complex numbers, a plus bi, and that equals c plus di, when is this going to happen? What's going to be true if a plus bi equals c plus di? A equals c, and b has to equal d. And what we can say is the real part has to equal the imaginary part. That's the only way that they're going to be equal. So I could say if a plus bi equals c plus di, they're the same thing. And most of this is complex numbers act essentially like all the numbers we've worked with before, so a lot of this is really intuitive. All right, questions? We good here? What we really want to talk about is operations. Holy moly, what am I doing? Upper A, operations. Is that right?
You'll be famous on YouTube, Mr. Beamer.
I think that word is infamous. It's the math teacher that can't spell. All right, so the first operation we want to talk about is addition. Operations, we're going to add, subtract, multiply, and divide. How are we going to add these two things? A plus C, and then plus B plus D I. So we add the real parts and add the imaginary parts. And that's why this is just relating back to the way we already worked with, first semester, the way we worked with complex numbers. This is like the x component and the y component of a vector. That's kind of why we think of them that way. All right, so let's do a couple of examples. Easy examples. 6 minus 3i plus 1 plus 2i. So what is that going to give us? 7 minus I. 6 plus 1 is 7. Negative 3 plus 2 is negative 1. And we write it in standard form. What if we were subtracting? What if we had 5 minus I minus 2 minus 4i? So what are we going to get here? 3 plus 3i. 5 minus 2 is 3, and negative 1 minus negative 4 is positive 3, and that's going to be our imaginary. Easy, right? So what would we have to add? What would we have to add to 3 plus 3i to end up with 0? Just what would we have to add? What complex number would we add to this number for the answer to be 0? Negative 3 minus 3i. When we add two numbers together and we get 0, we call them additive inverses of each other. So like negative, that's a fancy word for saying the negative. Negative 3 is the additive inverse of 3. 2 is the additive inverse of negative 2. So I think one of your homework questions asks you about the additive inverse. This means what number do you have to add to the number that you have to get 0. All right. So one of the nice things about complex numbers is there a lot of the properties that we use with real numbers are true for complex numbers. We can distribute. We can use the associative property. We can group them. We can use the commutative property. We can move things around. So that's how we're going to end up doing multiplication. So let's talk about multiplication. What would we do if we had 2 times 7 minus 5i? 14 minus 10i. We would distribute the 2. So intuitive, just like we would think. So let's extend that and say what would we mean then if we were saying 3 minus I times 5 plus 4i. What are we going to do here? FOIL. We're going to FOIL this. Foiling is a way for us to remember how to distribute properly. So we're going to FOIL. So we're going to do the first. 3 times 5 is 15. Outside we get plus 12i. Inside we get minus 5i. And last we get minus 4i squared. And we're going to combine like terms. Combine the real parts and the imaginary parts. So I get 15 plus 7i. And I squared is negative 1 times negative 4 is plus 4. So we finally end up with 19 plus 7i. So we FOIL that. So remember that I squared is negative 1 and you'll be fine. Are we good there? Yes? Feeling good? All right. It's a good thing before you have to go to the dentist. It's a good thing to feel good. All right. So I'm going to say if I have 1 plus 7i squared, I'm going to say this is, tell me if I'm right or wrong. Is this 1 squared plus 7i squared? No? What do FOIL, I only have one thing. No? This is telling multiply it by itself, right? 1 plus 7i times 1 plus 7i. And what do we get here? First, I get a 1 plus 7i plus 7i, I get a plus 14i minus 49i squared. I usually write out this last one just so I don't make a plus. Or I could just get rid of the I squared, right? All right, and 49i squared is negative 49 plus 1 is negative 48 plus 14i. All right, let's do one more.
Always the last one.
Yeah, I was just going to say, does it matter what way we put it in?
Our book, well, normally we write it in standard form, where the I comes last. And our book always writes it in standard form. So that's like writing, when we write polynomials, we write the exponents in decreasing power. So it's kind of our convention, is to write it. No, I would not mark you wrong for writing in the opposite order. Let's, one more. So for What happens if I get something like this? 4 plus 5i times 4 minus 5i. What are we going to get here? 16. And I get a minus 20i and a plus 20i. So those go away. So I get a minus 25i squared. So I end up with 16 plus 25, which is 41. I end up with a real number. No imaginary part. Do we remember what we call complex numbers that are related like this? Where the sign on the imaginary part is opposite. Well, that's what we did here. Is we did we end up with a difference of squares. I think that's what you were thinking. The conjugate. These two are conjugates of each other. So that's the next thing we're going to talk about. Complex conjugates. So if we have a plus bi, to get the complex conjugate, we change the sign on the imaginary part. We change that to a minus bi. And complex conjugates are important because of this property. When I multiply a complex number by its conjugate, I end up with a real number. So we end up using complex conjugates when we divide complex numbers. So we're good with the concept of a conjugate. And we remember way back when we were doing trig identities, and we had something like 1 over 1 minus sine theta, and we multiplied the numerator and denominator by 1 plus sine theta to simplify that. Remember doing that? Some people are sound like it's a painful memory. That's how we're going to do division with complex numbers. So if I have 2 divided by 1 minus I, I'm going to multiply the numerator and denominator by the conjugate of the denominator. So I'm going to multiply by 1 plus I, and I'm going to write parentheses so I remember to distribute properly. And now we're going to simplify this. So in the numerator, what do we get in the numerator? 2 plus 2i. And in the denominator, 2, I get 1 plus 1i minus 1i, the i's go away, minus I squared, so I get 1, I'll write it out, 1 plus 1 equals 2 plus 2i over 2. Can I simplify that? Can I reduce that fraction? 1 plus I. So 2 over 1 minus I is 1 plus I. Kind of an interesting thing to think about dividing by a complex number, isn't it? So to do division, we're dividing the numerator and denominator we're multiplying the numerator and denominator by the conjugate of the denominator. So let's do one more example. 2 minus I over 4 plus 3i. So put parentheses here. What are we going to multiply by? 4 minus 3i. And often this is the case when you're solving some kinds of problems in math, where you end up multiplying. I always call it multiply by a convenient form of 1. Because 4 minus 3i is over 4 minus 3i just equals 1. But it's a convenient form of 1. It's one that helps us out. All right, so let's simplify this. So what do we get here? We get 8 minus 6i minus 4i plus 3i squared. I usually have to write out, or I encourage you to write out a few steps here. Don't try to combine them all into one. It's easy to make a sign error, a positive or a negative, get it wrong. And on the bottom, we end up with 16 minus 9i squared, so we get 16 plus 9. So in the top, I get 3i squared is negative 3. So I get 5 minus 10i over 25. Can we reduce this? Divide everything by 5. 1 minus 2i over 5. I would be fine with your answer in this form, but standard form, and your book always writes everything in standard form, I need to write it as two separate fractions. 1/5 minus 2/5 I. Your book will always write it in this form. I'm fine with this form. But this, technically, if the problem says write it in standard form, this is standard form. All right, we good there? Okay, one last little detail. When you use the quadratic formula, so you're solving a quadratic equation, you end up with a quadratic formula. You end up taking the square root of a negative number. So the square root of, I'm going to say negative a, where a is a real number greater than 0. The way we do this, and we've done this for a long time. I'm just going to write out how we think about it when we do this. This is the same as the square root of negative 1 times a. And we can separate that out. The square root of negative 1, not negative square root of 1, square root of negative 1 times the square root of a. And our book always writes this as square root of a I. And it's kind of frustrating because it's hard to tell when you see it typed out whether the I is under the square root or not. I usually write this I square root a. So we take the square root of the negative 1 and we take that out of the square root, and it's square root of a. And when we use the quadratic formula, we write that plus or minus, because we can get the plus or minus when we take the square root of a real number. So that's why we write it that way. But just be aware that your book is going to write it square root of a I. And sometimes it looks like that I is under the square root. But for what we're doing here, we're not taking the square root of imaginary numbers. We know how, right? We'd have to write it in trig form and raise it to the 1/2 power. Okay. Questions? All right, homework. That is it. I know you guys are disappointed. There's an hour left. We have a time to do a whole nother lesson, don't we?
Yeah.
All right, there you go.